All right, yay, this is our next to last section. So here we go, section 6.2 called orthogonal sets. So a set of vectors is called an orthogonal set if basically everything is perpendicular to everything else. So when you test it, you test, let's say you test these two vectors right here. Oh my gosh, sorry. All right, you test these two vectors right here. You do their dot product. So we'll call this like u, v, and w. How about? So u dot v. Well, if I dot those together, I get 0. If I dot u dot w, I also get 0. And if I do v dot w, I also get 0. So since all three of those things check out and they're all perpendicular to each other, then this is an orthogonal set. And let's see, let's call these ones right here also u, v, w. When you do the first two, u dot v, you get negative 20 plus 4, or minus 4, plus 0, plus 24, so that's looking good. But if you do v dot w, you get negative 12 plus 3 minus 15 minus 8, and that minus 15 in there, that is not 0. So this one checks out. This one is a no. All right. So theorem 4 says, suppose you have an orthogonal set of non-zero vectors, then you have a set that is linearly independent, and also then a basis for the subspace spanned by that set. All right. The next thing says an orthogonal basis is for a subspace W of Rn is a basis for W that is also an orthogonal set. So if you call something an orthogonal basis, then it's also an orthogonal set. So meaning that they are perpendicular to each other. All right, so show that this is an orthogonal basis. So I have to show two things basically, that like u1 dot u2 are equal, the dot products equal to 0. So then u2 and u3 and u1 and u3. So if you do the dot product, those do in turn each equal 0. And so also then if you RF this, if you put this in a matrix and RF it, you will see that it comes out to 1, 0, 0, 0, 1, 0, 0, 0, 1. So you can see that it is a basis for R3, and because they are all orthogonal to each other, that's why it's an orthogonal basis. All right. All right, so that's just the gist of the beginning here. Now we're getting into some stuff that's going to be a little bit strange, but if you follow along, it's not that hard. It's just a little bit kind of weird. All right. So anyway, theorem 5. If you have something that's an orthogonal basis for a subspace, then each y, so each thing in that subspace, has a unique representation as a linear combination of those vectors. So basically, this next example is saying to you, you have this vector y, and we want to know how do you take these three vectors and basically linear, like what linear combination of these three things comes out to this answer. And so what we're going to do is we're going to call this basically u1, u2, and u3. So my question is this: y is what times u1 plus what times u2 plus what times, another thing, plus what times u3. Okay, so what we're trying to find, we know u1, u2, and u3. What we're trying to find is what constants I have to put in front of those things. And so we're going to end up with an equation. All right, so what this is telling you up above here, to find those values of C, this is what you do. So basically these are telling you the coefficients to put in front of your basis vectors to linearly combine them to be the vector that you started with, okay, to this y vector. So what I do, so if I want to find C1, I would take y, which is the 3, 7, 4, and I would dot it with u1 over, I would do u1 dot u1. All right, so let's dot y with this guy right here. So that would get me 3 minus 7, so that's negative 4, over u1 dot u1 is like 1 plus 1, so that's 2, so negative 2. So I have found out that y equals negative 2 u1. All right, C2 is y dot u2 over u2 dot u2. So y dot u2, so that's this one right here. So it'd be 3 plus 7, so it'll be 10. And u2 dot with u2 is 2, so it's 5. So this is going to be plus 5 u2. All right, and the last one, C3. So y dot u3 over u3 dot u3. And y dot u3, so that's with this guy right here, so it's just going to be 4. So I got 4 over, that turns into 1, the dot u3 dot with u3, so that's 4. So plus 4 u3. So if you were to do negative 2 times this vector plus 5 times this vector plus 4 times this vector, you would get y. That's all that's saying right here. So this right here is the answer that you're interested in for that question. All right, so now this next part deals with projections. Now projections are not my favorite thing. They're always a little bit strange to me, but let's see if I can break this down for you. So a projection is this. Remember, a projection vector is like the shadow that a vector that you have, a vector that you know of, it's like the shadow that it makes along a path that is chosen for you. And what you're trying to do when you do the projection is the shadow that it makes. So basically, it's the part of the vector that goes along this new path, but it is only a piece of that new path. All right, so it only like goes to right here. And so what you're trying to do, that's the projection of the blue one, is the projection of the red onto the path that's right here. And then what you do is you have to also find the other vector, the vector perpendicular to this, that is acting to make up the red vector. So you're finding this one right here as well. So the green one and the blue one, they are perpendicular to each other. Okay. The blue one down below, that is the projection vector, right? The green one is just perpendicular to that. And you would also know that the blue plus the green equals the red, right? So the red is the one you're given. You do the projection to find the blue one. And then if you did basically the red minus the blue, that would get you the green. So that's what's going to go on here in the next little bit. Okay, so let's read over here. For a non-zero vector u in Rn, suppose we want to write y as the following. We want to write y, so that's this guy right here, as a multiple of u. So remember, u is like going in this direction. In this direction here, as a multiple of u plus a multiple of a vector perpendicular to u. So that would be this guy right here. So we're trying to break it down into these two pieces. All right. So what you're going to do to figure out this blue piece over here, that you're going to do projection. If you go back to when we did projection before, you remember it was these dot products right here. And so that is going to be the part, basically the blue vector. And to find the green one, we already know the red one, so we're going to do the red minus the blue to get us the green. Okay? All right, so let's see if we can't do this example. It's not going to be that hard when you see an example. All right, so we have compute the orthogonal projection of 1, -1. So this 1, -1, this is our y vector. Okay? All right, and onto the line through -1, 3 and the origin. This is our u. All right. So we want to calculate y hat. So that is y dot u. So if I dot these two, 1, -1 dotted with -1, 3, I get -1 plus -3, so I get -4 over u dot u. So u dot u will be 1 plus 9, so it'll be 10. And then that's all multiplied by u again. So multiplied by negative 1, 3. All right, so that's negative 2/5 times negative 1, 3. So let's see, when I do that, I get 2/5 for my first part and then negative 6/5. All right. So remember that what we just found right there, we just found this blue part right here. And so the red minus the blue equals the green, and I need to find the green piece right now. So if I do the red one, which is originally y, so if I do 1, negative 1, minus this projection I just found, minus my 2/5 and negative 6/5, this is going to get me basically what they're calling up here, z, I guess you could say, right up here. All right, so 1 minus 2/5, I get 3/5, and negative 1 minus negative 6/5, that would be positive 1/5. Okay, and so that right there is z. All right, and so what you've just done, y is equal to y hat plus z. So let's see if we can piece it out for us here. So y is 1, negative 1. We have broken it into two pieces. Y hat, which is 2/5 and negative 6/5, plus z, which is 3/5 and 1/5. Okay, so if you actually add those together, you see it does make 1, negative 1. And so what you've done is you've broken it up into two pieces. These two pieces are orthogonal to each other, okay, and they add up to the original vector. Okay, all right, so I think we probably did a little bit too much for what it asked for, but just so you understand the whole picture. All right, so for this example here, right, y is the sum of a vector and a vector orthogonal to u. So basically what I finished up doing on the last example, I kind of went too far, but that's what we're going to be doing here. So let's just do this all one more time. So first I need to find y hat. So remember, y hat is the projection vector. So I have to do y dot u. So I'm going to do 2 times 7, so 14, plus 6 times 1, plus 6, so that'd be 20, over u dot u. So that'd be 7 times 7 and 1 times 1 added up, so that'd be 50, and then multiplied by u again, so 7, 1. So that turns into 2/5 times 7, 1, so I get 14/5 and 2/5. All right, so now we have to find, so if I kind of go with that picture we had before, this was y, this was my projection, and this was z right here. We just found the projection vector. All right, so now I have to do y minus that to get my z. So y minus y hat equals my z vector. So 2, 6, oh geez, that's not right, hang on. 2, 6, that vector, minus the 14/5 and the 2/5 is going to be what I want. So let's put everything in fifths. 2 is going to be 10/5, 6 is going to be 30 over 5. So that would be 10/5 minus 14/5, that'd be negative 4/5. And then 30/5 minus 2/5, that's 28/5. All right, so we have it. So this question said to write y as the sum of these two things. So y equals my 14/5 and my 2/5 plus my negative 4/5 and 28/5. And if you check that out, these are perpendicular to each other. So if you did their dot product, you would get 0. All right, and let's see, if you add those up, you get 10/5, which is 2, and you get 30/5, which is 6, which is exactly what y is. All right. All right, so just another last little bit right here. A set of vectors is called an orthonormal set if it is an orthogonal set of unit vectors. And so the last example that we have to do is basically kind of inspect what orthonormal means and if something's an orthonormal set. So not only do they have to be perpendicular to each other, they have to be unit vectors. All right. So first, let's check and see if they're perpendicular to each other. That's what we're doing here. So let's call this one u and v. So we'll do u dot v. So if I do negative 0.6 times 0.8 and then plus, then I would do 0.8 times 0.6. It's obvious that that comes out to 0. So that checks out. Okay. The next thing I have to check is the magnitude of each one, 1. So the magnitude of u. So the magnitude of u, I would get negative 0.6 squared plus 0.8 squared. So it's going to be 0.36 plus 0.64, which adds up to 1. And so, yes. And you can see that basically magnitude of v is the same thing because it's just 0.8 and 0.6 and the negatives aren't there anymore, but it's okay. So we'll just put magnitude of v is equal to 1 here. So that checks out. All right. So we don't have to do what it's asking right here to normalize it, which we will have to do on the second one. So we'll call this one u and v. So first of all, let's just check out. So u dot v, let's see if it's equal to 0. So negative 2/3 times 1/3 is negative 2/9. 1/3 times 2/3, that's 2/9. And the last one is 0, so that checks out. Now, the magnitude of u. So magnitude of u would be 4/9 plus, oh, and I forgot over here, this is supposed to have a square root on it, but it doesn't matter because it's 1. So anyway, this is the square root of all this. So 4/9 plus 1/9 plus 4/9. Well, that's 9/9, so that's square root of 1, which is 1. So that works out. But there's a problem because the magnitude of v is not 1. That is the square root of 1/9 plus 4/9. So that's the square root of 5/9. So it's not equal to 1. So this is not an orthonormal set. We have to make it that way. So to make it that way, what we have to do is we have to turn the bad one, v, into a vector that has length 1. And so to do that, we just turn it into a unit vector. And so remember, to turn something into a unit vector, I just have to divide it by its own magnitude. Well, we figured out up here that the magnitude of this thing, if I do that, is the square root of 5/3. Okay, so we just have to basically divide everything in v by square root of 5/3. So to divide by square root of 5/3 means to multiply by 3/5. All right. So what I would do is I would keep u, negative 2/3, 1/3, and 2/3. And then for v, what I would do is I would divide everything by radical 5/3. So, but when we divide something, let me just show you here. If I take and divide something by radical 5/3, I'm really multiplying by 3/radical 5. So x times 3/radical 5, which means if I rationalize, I have x and then 3/radical 5/5. So that's what I'm going to multiply everything by, just to keep it rationalized. So I have 1/3 times 3/radical 5/5, so that becomes radical 5/5. Then I have 2/3 times 3/radical 5/5, so that becomes 2/radical 5/5. And the last one is still 0. So if you were to check this out, it would be still perpendicular to this guy right here, because we did not change its direction, we just changed its length, its magnitude. And this one already had a magnitude of 1, and if you did it, you would find that this one now has a magnitude of 1 also. So now this is an orthonormal set, and we have normalized it so that to make it so. All right. And then down here are just some extra little things to read through right there. And then you got these 4 problems to do in the book.